Hello. Today I'm going over AICE Physics Syllabus Code 9702, Paper 21 from October-November 2016. Question number 4 reads, state what is meant by the frequency of a progressive wave. You can see here I've got the definition of frequency, the number of oscillations per unit time. Another way to think about frequency is number of waves per second. So the second is the unit of time, and so waves per second, to just have something easy to recall to mind, but a sort of a more formal way to think about that, oscillations per unit time. Waves per second. Part B reads, a cathode ray oscilloscope, CRO, is used to determine the frequency of the sound emitted by a loudspeaker. The trace produced on the screen of the CRO is shown in figure 4.1. The time base setting of the CRO is 250 microseconds per centimeter. Show that the frequency of the sound wave is 1600 hertz. Oftentimes it's helpful to just write down what's given, and so the time base setting is 250, and micro is the same thing as 10 to the negative 6. It's a millionth. So 250 microseconds per centimeter. If we look at the cathode ray oscilloscope, figure 4.1, one of these squares here is 1 centimeter, and it looks like the most convenient place to read this is at this peak right here, neatly intersecting this division. And so if we go over from this peak, 1 centimeter, 2 centimeters, 2.5 centimeters from crest to crest. So that's one waveform, so there are 2.5 centimeters per wave. By setting up the calculation like this, we're going to cancel out the unit centimeters, and we're going to have seconds per wave if we multiply 250 microseconds times 2.5 centimeters per wave. Remember that the time-based setting tells us how much time each division in the oscilloscope represents. In this case, 250 microseconds for every one of these centimeters. By multiplying those values, we get 250 microseconds times 2.5 centimeters per wave. That gives us 6.25 times 10 to the negative 4, and the units here are seconds per wave. Now, how many seconds per wave is the definition of period? We're asked to show that the frequency of the sound wave is 1600. So remember that frequency is just 1 over the time period t, and so 1 divided by 6.25 by 10 to the negative 4 seconds should give us the 1600. Since that value is already in the calculator, you can use the inverse key, right? Frequency and time are inversely related. Some calculators will have a key, maybe 1 over x or x to the negative 1, same thing. And so there we've shown that the frequency is indeed 1600 hertz. Part C reads, the loudspeaker in B emits the sound in all directions. A person attaches the loudspeaker to a string and then swings the loudspeaker at a constant speed in a horizontal circle above his head. Why not? Let's just, connect a speaker to a string and swing it over our head in a horizontal circle. This further illustrates my point about the absurdity of these Doppler Effect questions, but we'll just keep going on with the calculation. An observer standing a large distance away, well, thank goodness, from the loudspeaker, hears sound of maximum frequency 1640 hertz. The speed of sound in air is 330 meters per second. Determine the speed of the loudspeaker. I can't stress this enough how this is a theoretical calculation and not lab work. Here we're going to use the Doppler effect. Remember that the Doppler effect is, there's an equation governing the Doppler effect, and that equation is indeed one of the ones that is provided to you on the list of formula as you sit for the AICE Physics papers. And so the Doppler effect is the observed frequency is equal to the frequency of the source times the speed of the wave divided by the speed of the wave plus or minus the velocity of the source. Because we're solving for the speed of the loudspeaker, we can think about it like this. The observed frequency is the frequency of the source times the velocity of the wave over the velocity of the wave. And because the observed frequency is higher, we know that we're subtracting here in the denominator in order to make that value larger. So this would be when the maximum frequency is when the speaker is moving towards the observer, right? So we're subtracting in the denominator. Substituting in values, we've got 1640 hertz equal to 1600 hertz times 330 meters per second, the speed of sound, divided by 330 meters per second minus the velocity of the source. Multiplying both sides by that term, we get 1640 hertz times 330 meters per second minus the velocity of the source equals 1600 hertz times 330 meters per second, dividing each side by 1640 hertz. We get 330 meters per second minus the velocity of the source equal to 321.95, subtracting 330 from both sides. We solve the velocity of the source as 8. The question goes on to read, describe and explain qualitatively the variation in frequency of the sound heard by the observer. Well, because the person decided to swing the loudspeaker at a constant speed in a horizontal circle above his head, the observer, being a long distance away, is going to hear the frequency vary between 1600 up to the maximum frequency 1640, and then it's going to get lower than 1600 as the speaker moves away from the observer. So it's going to, the frequency heard will sort of move up and down as the speaker moves towards and away from the observer. I'll leave it to you to put that in your own words.